A massive steel arm snaps down on a cold factory floor. Heavy iron gears grind against each other as hot sparks fly into the dark air. Deep inside the spinning machinery, friction builds up far too fast. A single metal bearing gets scorching hot, swells up, and freezes solid. Within seconds, the entire assembly line comes to a complete, violent halt. Red emergency lights flash along the high ceiling as workers stand silent. Every single minute this assembly line stays quiet costs the manufacturing company thousands of dollars in lost product. Maintenance workers scramble across the concrete floor to open heavy steel doors while smelling burnt industrial oil. They do not know which small internal gear failed deep inside the iron box. Finding the broken component takes hours of dangerous labor, while delayed shipping dates ruin business commitments across the globe. Small, durable blue boxes now sit mounted on every critical joint of that heavy steel machine. These small hardware units are live IoT sensors. They constantly listen to every tiny mechanical vibration and check the surface temperature hundreds of times every single second. They never sleep or lose focus. They measure tiny micro changes in movement and heat that no human skin or eye could ever catch on the shop floor. The live stream of information travels at high speed through fiber cables attached to the structural ceiling beams. It leaves the noise, smoke, and danger of the physical factory floor far behind. Millions of clean data points rush into secure server rooms located miles away. Inside those cool rooms, quiet black server racks swallow the incoming numbers instantly, bridging the wide gap between cold iron and digital code. Inside a high-resolution computer screen, a complete digital duplicate of the manufacturing plant floor comes to life. Every conveyor belt, robotic arm, spinning shaft, and mounting bolt appears on the screen in precise visual detail. This complete online creation is known as a digital twin. It does not simply look like the real building. It moves, heats up, and reacts in exact lockstep with the real machines. If a physical conveyor belt speeds up by 2% on the floor, the virtual belt inside the model accelerates instantly to match it. The virtual duplicate uses real-time operational data to simulate natural laws like total mass, friction, and heat transfer. Engineers can walk through this computerized facility without wearing hard hats or heavy boots, observing how thousands of intricate components interact without any risk. Advanced software packages make this deep virtual connection possible. Using specialized tools like Siemens Xcelerator, plant engineers can construct and run detailed simulations of massive production lines. The software tracks every moving mechanical element across thousands of square feet of workspace. It converts complex physical processes into clear lines of structured computer data that can be analyzed and adjusted with a simple keyboard command. When an engineering team wants to test a faster line speed, they no longer adjust the real machinery on the floor. Instead, they change the velocity parameters inside the virtual simulation first. They intentionally push the computer model past its normal operational limits to see where the system breaks down. If a virtual gear snaps under stress, zero real metal is destroyed, and no workers face danger. Computer algorithms can run thousands of these high-stress testing scenarios in a matter of seconds. The simulation tests extreme ambient heat, maximum cargo weight, and sudden electrical power loss all at the same time. It identifies the exact performance limit where machinery stays safe while maximizing total output. This rapid testing cycle delivers complete optimization before any physical change is made to the plant. Zooming out beyond an individual machine reveals the massive power demands of the broader manufacturing facility. Hundreds of heavy electric motors draw immense current from the local utility grid every morning. When every motor fires up at the exact same moment, electricity bills skyrocket due to peak demand surcharges. The virtual system maps this heavy power draw across the entire plant footprint with complete clarity. By studying the virtual copy, plant managers can stagger the startup schedules of heavy machinery across different shifts. The digital twin demonstrates exactly how to balance the electrical loads smoothly throughout the day. This simple scheduling adjustment slashes monthly energy costs without reducing overall manufacturing volume. Smart adjustments in operational timing save huge operational funds without requiring the purchase of a single new machine. On the actual factory floor, a technician walks down the central aisle carrying a lightweight handheld tablet. The worker no longer carries heavy metal wrenches or greasy paper instruction manuals. The bright screen on the tablet displays a visual overlay directly on top of the physical machine standing in front of them. Green highlights indicate healthy components, while yellow warnings point out parts requiring inspection. Operators no longer need to wait for a loud snap or a thick plume of smoke to identify a failing part. They no longer guess which joint needs grease or which hydraulic line is blocked. The software provides exact diagnostic facts long before physical damage occurs. The daily anxiety of sudden line failures disappears from the factory floor as workers gain complete foresight over their equipment. This forward-looking maintenance strategy is known as predictive maintenance. The digital twin detects subtle changes in sound waves and thermal radiation weeks before a metal surface physically bends or cracks. It calculates the remaining operational life of a bearing down to the exact day. Maintenance teams order replacement parts far in advance and install them during scheduled breaks, completely avoiding costly emergency shutdowns. The positive operational impact extends far beyond the perimeter walls of the local manufacturing site. Down at regional ocean ports, massive container ships wait for cargo arriving from inland assembly plants. When factories operate continuously without sudden breakdowns, transport trucks reach the shipping docks on exact schedules. Global supply chains avoid sudden inventory gaps, keeping store shelves stocked with necessary goods without costly logistical delays. Overall factory throughput rises significantly as production equipment operates smoothly for months without unexpected halts. Raw materials move continuously through every stage of assembly, turning into finished products at a steady, predictable rate. Eliminating random mechanical stops allows industrial companies to generate far more finished goods using their existing physical machinery, turning the plant floor into a precise, dependable system. Every hour of production creates a richer data stream between the physical plant and the computer network. Live IoT sensors constantly feed fresh operational metrics into the virtual twin. The computerized model compares real performance against historic operational trends to make future predictions even more accurate. Over time, the system becomes increasingly effective at identifying hidden inefficiencies before they can affect production. Traditional industrial plants were once rigid structures made of stubborn iron hardware that took months to modify. Changing a plant layout required heavy rigging, long installation periods, and expensive trial periods. Modern digital twins transform those heavy physical systems into flexible software environments. The entire manufacturing facility becomes a fully programmable system that can be debugged, reconfigured, and refined inside virtual space. Consider a facility manager who must integrate an entirely new product line into an active manufacturing building. In past decades, this task required shutting down active assembly lines for weeks to clear floor space and install new conveyor tracks. Spatial errors often meant expensive robotic units would not fit properly or would block critical safety walkways during daily operations. Today, that entire retooling process takes place inside the virtual simulation space long before equipment is ordered. Engineers position new virtual machines onto the digital floor map and simulate the complete material workflow. They run 6 months of full-capacity production tests in less than 5 minutes, discovering spatial bottlenecks and safety hazards, while the physical factory continues running without interruption. This virtual testing approach saves industrial enterprises millions of dollars in potential errors while drastically reducing material waste. Less steel and plastic are scrapped during prototype phases, and less power is wasted on failed production runs. The unmatched precision of virtual simulation makes modern industrial production cleaner, safer, and far more resource efficient than ever thought possible in traditional manufacturing. The true power of digital twins rests in this invisible bridge connecting clean computer code with heavy industrial machinery. By creating an accurate virtual model, engineers gain complete control over complex physical processes once governed by chance. Industrial production is no longer constrained by mechanical surprises or unmeasured wear. The virtual model leads every step forward, guiding physical hardware toward total operational perfection.